Okay. So just so you know, when we get back, there won't be a video to watch. There won't be an in-class quiz. So there'll just be, I guess there's a couple of, there's sapling is up on the sapling problems. They're due, I think, the Wednesday when we get back. So they're due next Wednesday. So I guess if you have some, I need to be away from the family time, you can always try those. Okay, so there's more reactions that we need to talk about for the additions to double bonds. And I think this may be the first part of this will be the tail end of the lecture notes that were online the other day. And then there's some new reactions after that. We'll go through these, and then this is where I'm going to pick up when we come back. I also have given you some problems for practice problems for writing the products of reactions that we've kind of already gone over, or we will go over today. And so you could write the complete reactions for those, and then I don't know in the directions it doesn't say. Well, it says in the second part, is it regio, stereo, both or neither? And I just released this morning, there's an written answer key for that, and then there's a narrated key for each one of those problems. So if you can try those to get the stereo, regio, and if not, there's full-blown narrated versions. So let's talk about another way to add H and OH. So this is called mercuration, demercuration. And basically, sadly, these notes are kind of messed up. So that should be an Hg. That should be an O acetate. That's attached there. Here is my Hg again. And here is my O acetate. And then here is my OH. So I don't know why I did that, but it did that. And then up top, there's another Hg and an O acetate bonded to the Hg. So first of all, we're going to take mercury 2+ ion. So it's mercury 2+, and then the OAC, what does that stand for? Well, that stands for basically a deprotonated acetic acid. So what I'm doing is I'm reacting an Hg2+ ion. There's 2 acetate counterions with that. And that's acetate because that's one of the mercury salts that's actually soluble in things. So when I look at this, I have mercury acetate and water. So our electrophile is going to be the mercury, and our water is going to be the nucleophile. So again, we are adding electrophile first, followed by nucleophile. Only in this case, I've now made the electrophile a mercury ion. And so we can kind of think of this reaction happening like this. There's the mercury ion, and basically it's attached to 2 acetates as a counterion. So what we can think of is we can think of either this being an Hg1 acetate plus, because if I lose 1 acetate, I get a +1 ion. Or we can think about, let's take this double bond, let's bring its electrons to bond the mercury, and then we kick off an acetate group as a leaving group. So what I would make is I would have the carbon bonded to the mercury, which is then bonded to the other acetate. And my other acetate would then leave as a leaving group. So there's my triangular intermediate. And I'll just go right to the triangular intermediate. Mercury is big enough, like bromine, where it can sit on top of the double bond. And it can simultaneously bond to both carbons. And so that means that this, I guess, mercurium ion is going to have the same characteristics as a bromonium ion. The mercury is big enough to sit over both carbons. Both carbons are going to share the delta plus charge. And now I have a triangular intermediate, which is going to set the stereochemistry to be, what was the triangular intermediate stereochemistry yesterday with bromine?
Trans. You have to go from the opposite side.
Right. So anytime you have a triangular intermediate, the electrophile will add to the top, and the nucleophile has to add underneath. And the same thing's true here. So this reaction could be stereoselective, because I will have 100% trans addition. Okay? Because of that triangular intermediate. Now, basically, I could rewrite this as, this thing's all messed up. I can basically think about this as my mercury ion. Let me come over here and rewrite that. And I usually write the acetate like that. I've got 2 delta plus charges on the carbon. Now my water is going to come in and add underneath, just like the Br minus did yesterday. And then the pair of electrons will go to the mercury, so that now I will end up with the carbon attached to the mercury. On one side, my oxonium ion, then added to that carbon. Okay, so this will be the intermediate. Then I'll lose the H plus off the oxonium ion, so that I will make my mercury acetate, my C with my OH, so that I'll end up now with this intermediate. So I normally would just say, well, I'll add the water in 2 steps and get an OH added, but I've shown you explicitly that I'm forming the oxonium ion because I want you to remember that. All right, so now we're sitting there, which is what that's what this should be. This should be C with the mercury, with the C with now the OH down here, and then the acetate there. So the critical thing here is that the mercury added, the mercury and the OH are trans. They've added trans because this went through a triangular intermediate. Now, to get rid of the mercury, we use a reagent called sodium borohydride. And sodium borohydride is the sodium, the BH3, or B, this has 4 hydrogens attached to the boron. It turns out that hydrogen is actually more electronegative than boron. So that in this structure, this BH4 minus ion, the hydrogens are delta minus, and the borons are delta plus. And that's why it's called borohydride, because in essence you have an H minus ion. And that's called a hydride from way back in general chemistry. So sodium borohydride basically is a source of H minus. We're not going to talk about this second mechanism other than to say this. The sodium borohydride replaces the mercury with a hydrogen. with retention of configuration. So in other words, the mercury and the OH were trans, and when the sodium borohydride reacts with the mercury, the H and the OH are still trans. So the initial geometry then of how the mercury added is carried through with the hydrogen. So in the end, I've added H and OH trans to the double bond. How much? 100% trans. So it's like bromonium ion. It's like bromination. Again, because it goes through the triangular intermediate. So we're going to end up with these triangular intermediates, and then we're going to relate them to epoxides, which will also have triangular intermediates. So I want you to remember that, the idea that when you have a triangular intermediate, trans addition. But it can only be triangular if the atom is big enough to basically bond to both carbons. So bromine and mercury are big enough to do that. Hydrogen isn't. Hydrogen's got to make a choice. Okay, everybody's kind of with me? So here is my triangular intermediate. So what I just did was I just kind of set the stereoselectivity, right? H, OH. When we do mercuration, demercuration, we go back to what I said yesterday, which is getting kind of boring. What do I add? H and OH. How do I add it? Well, let's come back to that. How do I add it? 100% trans. Now let's go back to the Markovnikov, anti-Markovnikov. And if we read the notes, it says it can be regioselective because it follows Markovnikov's rule, and it can be stereoselective because the H and the OH had trans exclusively or 100%. So how do we get the Markovnikov addition out of this? First thing you might say is, well, is there really Markovnikov addition? Well, yes, because in the overall reaction, I'm adding H and OH, and the H will add to the carbon with the most hydrogens, and the OH will add to the other one. So it does fit Markovnikov's rule, but yesterday I said, well, okay, we can broaden Markovnikov's rule and say the electrophile adds to the carbon with the most hydrogens, and then the nucleophile adds to the other one. So the mercury set the stereochemistry of this, and the mercury sets the regioselectivity. But there's a problem, and the problem is that I have a triangle. So how do I deal with Markovnikov's rule when I have a triangle? Let's just say, for the sake of argument, that I added this alkene, that I'm going to do mercuration and demercuration on that alkene. So it's not symmetrical. So and since each carbon in the double bond has an unequal number of hydrogens, there will be a Markovnikov product. And just to do it the way we've been doing it in the past, okay, mercury is our electrophile. So what could I do? Well, let me superimpose those two so that I don't get lost. Let's say, for the sake of argument, that I take and I add the mercury. Let's say I add the mercury to the left carbon, and I'm going to treat it as if I'm just adding the mercury like an H+. Let's forget about the triangle for a minute. So if I do that, then there's my intermediate. And I've got a CH3 here, an H there, an H there, and another H there. Right, so if I add the mercury to the left carbon, I get that one. And if I add it to the right-hand carbon, then I get that carbocation intermediate. So if I treat the mercury as if it was just an electrophile or an H+, I add it to both the left and the right-hand carbons, then I get those two intermediates. And now I could ask you, I could say, okay, which one of those two intermediates is going to be more stable? The left or the right? And someone would say, come on, somebody. Left? We all in agreement that the left-hand carbocation is more stable? I hope so, because what's the one on the right? Primary, and I'm not even supposed to write it, but I can't make a point without writing it. So this one's going to be more stable, which means that's going to lead to the major product. And so now what happens? Now what happens is my water comes in, adds to the carbocation, and in two steps, I get and I'm just going to write the mercury down here just because it has to be, it had to have added trans. And so that's my major product that I'm going to end up with my mercury and my OH adding trans. My water added formed the oxonium ion. I lose the H+, so I'm not showing both steps, but hopefully you remember they're there. So then what happens in the next step? The next step is I add my sodium borohydride. What happens to the mercury? It becomes an H, so that now I've added the H and the OH, Markovnikov, and trans. Okay. So I can treat this reaction as if it was HCl or H plus H2O. I can ignore the triangle if I want to get the Markovnikov or anti-Markovnikov product. If I want to show that this is Markovnikov, I can show that by ignoring the triangle. Except the problem is I can't ignore the triangle because that's what really happens. Because if the reaction went by this mechanism that I've shown you, what would happen? We'd end up adding the H and the OH 50-50 cis and trans. And we don't do that. So now we have to do is now we have to explain Markovnikov with the triangle. Okay. Everybody with me on the other mechanism? So now I have to say, well, how am I going to explain how am I going to explain this Markovnikov mechanism with a triangle? Well, I'm going to have to look at these two carbons, and I'm going to have to determine which one of those two carbons has the greatest delta plus charge. And you may say, why do you have to do that? Well, what kind of nucleophile? Well, actually, what I should do is normally what I would do is I would ask you, I would say, which carbon, A or B, is the nucleophile going to add to? It's got to make a choice. It's got to add to one or the other. Which one is it going to add to? How many people say it'll add to A? How many people say it adds to B? And the rest of you? Don't know? I won't even ask, don't care. Well, it's like an even split. of the people who decided to answer. Between A and B. But wait, which one does it add to? I already know the answer to that, don't I? Right, I already know it adds to A. So anybody who I'd say guess, but anybody who said B want to give me the reason why they think it's B?
I was thinking SN2.
And what about SN2?
Then it's going for what has the least steric hindrance.
So steric hindrance. So there was a time when I would do this, apparently that's not today, when I would just say, okay, without even going through this part of the mechanism and showing you what the real answer is, I would say, which one do you think it would be? And a lot of times the answer would be, well, it's going to add to B because B is less sterically hindered. And if you're going to say B, then you need to say what kind of mechanism is that? And you would say, well, it's SN2. But here's the problem.
It's not actually SN2. Yeah.
Right, it's not SN2, but why isn't it SN2? What kind of nucleophile do I have here? Weak. I've got a weak nucleophile. What kind of reactions do weak nucleophiles do? SN1. Now, don't forget about the steric hindrance, because if this reaction were to go SN2, that's going to be the major product. But I've got a weak nucleophile that can only do SN1. What dictates what rules in SN1? Well, carbocation stability. Right? In essence, the second part of this reaction is SN1. Now, how I got there is different than SN1, but the second part of this is SN1. Why did I choose this intermediate over the other one to be more stable? Because it's secondary over primary carbocation. Same trends as SN1. So the water is going to do an SN1-like reaction. In other words, this weak nucleophile, it's electron-rich, but it's kind of middle-class electron-rich because it doesn't have a full-blown negative charge. But the rules are still the same about electrophiles and nucleophiles. Here are my two electrophilic carbons. In chemistry, the nucleophile, the electron-rich, must donate to the poorest of the electron poor. It certainly isn't allowed to donate to another electron-rich species. Right? You could take that to your other classes where you can debate whether that's the same in real life or not, but in chemistry, electron-rich have to give to the poorest of electron poor. So that nucleophile is going to add to the carbon A or B that is the most delta plus, because that's the one that's most electron poor. And which one is that? Why? Why is it A? And again, we already knew it was A, right? So why is it A? Why does A have the most delta plus charge? I guess you weren't ready for that. The Y right afterwards, Joe.
The methyl group pulls a little bit of electron density away from the carbon.
Helps stabilize it, right?
Yeah.
In other words, if I looked at these two carbons, I would say this one looks like what kind of carbocation? A looks like a blank carbocation. A secondary. It looks like a secondary carbocation. Whereas B looks like a primary carbocation. Which one is more stable? The secondary. That means that the secondary is going to be able to have the most delta positive charge. And so the water's going to add then to the carbon with the most delta positive charge. It's going to add to A. And what happens here? The pair of electrons then goes to the mercury. So that in the end, my whole intact water molecule added down here. There's an H there. And then the mercury ended up there with the two H's, and I'm just trying to preserve the fact that the mercury and the OH and the water are trans. Joe?
If a carbocation were to form now with the mercury attached to a carbon, would that be considered a primary or secondary?
Well, the problem there is that it's going to be really difficult to form a plus charge on that carbon with the mercury attached, but it's primary because it only has one other carbon attached. So our rules are still primary, secondary, tertiary are dependent only on carbon. But to put a plus charge there would be really difficult. What's going to happen to the mercury? Sodium borohydride is going to do what to it?
Change it to an H.
Turn it into an H. So I end up with this product, right? Does that kind of make sense to everybody? I mean, we can ignore the triangle and just say, oh, I'll write the mechanism this way, but then that's not the real mechanism. The real mechanism has to have the triangular intermediate because that's the only way you get 100% transition. And so when we look at this triangular intermediate, we say, okay, I've got water. It's going to do SN1-like mechanism. What dictates the SN1 charge on the carbocation? Which carbon has the most delta positive charge? The one that is the most substituted. Nothing new there. And that's where the water is going to add. Okay.
What does this look like with all the transition states?
I think we would probably ignore the transition states at this point because the transition state for adding the mercury is going to look like the mercury ion. Okay? It's going to kind of look like that triangular, except, well, it's going to look exactly like that. Sort of.
So we don't have to worry about transition?
No, not for this. Not for this
What
one.
about for the other triangular intermediates that we have come?
I usually don't ask for transition states there either,
Okay.
but I do ask for all the intermediates.
So let's say that right carbon was a tertiary one, whatever with the water attack, that
Yep.
one.
There were two methyl groups on the right-hand carbon, on carbon B. That's where the water would add. If they were both secondary, 50-50. The key thing here is that this, since this is SN1, the only thing that it's going to follow is the charge. Sterics do not play a role. It's only the substitution. So it's only the charge. Does that make sense? So when we go back and we think about the bromine, there was actually that when you made the bromonium ion, we could have done the same thing with the adding the second Br minus, right? We could have said, oh, the Br minus adds to the most substituted carbon, but in that case, do we care? We don't care because we end up with two bromines. So we really didn't go through that part of the mechanism then because it doesn't matter. But now it does because I'm adding two different things through the triangular intermediate. When I do that, I got to pay attention to the Markovnikov rule. Does that kind of make sense? Yes? No? Well, we can do alkoxymercuration, demercuration, which means all I do is I substitute an ROH for an HOH. Same mechanism, except in the end, I'm going to end up with the OR group. So up here I would have my mercury and my acetate. And then in the end, I'm going to end up with the H in the OR group adding trans, but still Markovnikov. So it's an easy switch from H2O, HOH, to ROH. So I'm not going to spend a lot of time on that because the mechanism, just erase one of the H's and put an R there, and you've got the same mechanism. But that's a way to make an ether. So I can now add H and OR, Markovnikov trans. Now, why are these reactions important? Well, because there's going to be a slide, I think, that summarizes how to add H and OH. And one of the things we can do is we can now add H and OH Markovnikov, but 50-50 by adding H plus and H2O. But let's say I wanted to do a reaction. I specifically wanted to add the H and the OH Markovnikov and trans. Now I can do that. So there's two more reactions I need. I need to add anti-Markovnikov H and OH, which I'll get to. And then could I add it cis or trans? 100%. But we normally wouldn't do this. This is a really tough reaction in real life because mercury is bad, right? We all know mercury is bad. And mercury, doing this in a drug synthesis would be probably prohibited because, let's see, in drug synthesis there's rules about when you can use heavy metals, particularly toxic heavy metals, and you can't use them within the last X number of steps of a synthesis. And then you'd have to prove to the FDA that there's absolutely no mercury in the sample at all, which would be very difficult to accomplish that by their rules. So it looks great on paper, but we don't really use it. Right? Mercury is what? A neurotoxin. It causes either neuro stuff, right? And that can either be physical or it can be somewhat psychological as well. The Mad Hatter in the Alice in Wonderland. He wasn't angry. He was mad, meaning kind of crazy. And how did he get that way? Well, because he was a hatter. He made hats. And the way they made hats was they took mercury metal and they used it to sort of make the stiff brims. And so hatters worked with mercury with their hands a lot, and they eventually became mad. And that's where the term comes from. You know, we worry about mercury in the water. We worry about mercury coming out of the coal plant stacks. We used to worry about mercury in vaccinations, but that's been out of vaccinations for probably the last 10 years. That gets you into areas that I'm not going to go in. But we couldn't really use this reaction if we were trying to make a drug, because I think it would be impossible to satisfy the FDA that every atom of mercury is out. Okay, next reaction. Bromo Hydrans. So if I add Br plus and water, not just Br2, but I'm going to add Br2 and water, I'm going to end up adding a Br and an OH to form what's called a Bromo Hydran. I'm going to add it Markovnikov. So in this case, it's going to be a Br plus is my electrophile, and water is my nucleophile. So Markovnikov means the Br plus adds to the carbon with the most hydrogens, and the water adds to the other carbon, because it's the nucleophile. So here's my E plus, here is my nucleophile. So Markovnikov, 100% trans. How do we explain this? Well, if I organize this properly, I'm going to go back to the slides that I said before and say, okay, now erase all the mercury and put in a Br plus. And it'll be exactly the same mechanism. So then I can just move on. And actually I did that. So the mechanism for this is exactly what it was for mercury. What am I going to do? I'm going to add my Br plus. I'm going to add my Br plus to the double bond. And what am I going to make? I'm going to make a triangular intermediate. Just like you do for bromination. But now, when I do bromine and water, what happens is that the Br plus adds to the double bond, but since it's the solvent is water, the water's right there to add underneath. And so once I make my bromonium ion, my water's going to add. And so for this molecule, which would be, well, it'll be that molecule, where's the water going to add? To carbon A or carbon B? How many say A? B? Okay, that's good. It's going to add to the carbon that's most substituted, the one with the greatest delta positive charge. So that means that my bromine is not going to end up there. So in this case, my bromine is going to slide over. My oxonium ion is going to be here. There's my methyl group. There's my other methyl group. There's my H. There's my other H. And so I'm going to end up adding the bromine to the carbon with the most hydrogens, the water to the other carbon, 100% trans, Markovnikov trans. And then I'll lose the H plus, right, to give me the OH product. It's exactly the same as before.
But you don't have the, what was it, Borohydride?
Right, I don't have a second step. I don't have a second step to convert anything to the hydrogen. That's the only difference between the mercuration, demercuration, is you have that second step. But the critical part of the regio and the stereochemistry came in the first reaction with the mercury. After that, you just take the mercury off and put a hydrogen on with sodium borohydride. Unfortunately, sodium borohydride does retention. This one, I wanted to add the Br plus and the OH. So I formed this Bromo Hydran. Okay. Does that kind of make sense? All right, last one. So, I want to add H and OH. I've now got H and OH Markovnikov. What if I want to add H and OH anti-Markovnikov? Well, if I want to do that, I'm going to do what's called hydroboration oxidation. Hydroboration oxidation will add H and OH anti-Markovnikov 100% cis. And hydroboration requires BH3. Oxidation requires hydrogen peroxide, which is H2O2. So it's 2 reagents, 2 steps. Could be regioselective, could be stereoselective. All right, so here's how the mechanism kind of works. The boron and hydrogen bonds are kind of reversed, with the hydrogen being slightly negative and the boron being slightly positive, because that's the way the electronegativities work. So we can kind of think of the double bond electrons adding to the boron-hydrogen bond breaking, and the hydrogen adding to the carbon. And so when that happens, we add the BH3 across the double bond with a BH2 and an H. And that forms what's called an alkyl borane. Another way to think about this would be to think about the carbon-carbon double bond and then the boron and the hydrogen bond like this, where this pair of electrons goes to the boron and then the BH bond goes to the carbon. So you can kind of think of it as a square. It forms kind of a square transition state, because that transition state would look like this. That's what the transition state would look like, which is actually critical, that it's a square. So once I add the boron then to the carbon, to the double bond, then what's going to happen is, then I'm going to treat it with hydrogen peroxide, and by, again, another mechanism that I'm not going to get into, the BH2 gets converted to an OH. That's the role of the peroxide. So wherever the BH2 ended up, that's going to become an OH. And the hydrogen peroxide replaces the OH in exactly the same position as the boron added. So in the end, this is going to be 100% cis. Because again, the hydrogen peroxide, all it does is replace the boron. So whoever came up with these reactions, they decided to find reagents that would do retention as opposed to messing everything up by doing another inversion. Joe?
Why does the hydrogen move?
It didn't.
Okay.
It didn't. As I'm looking at this, I'm like, that blue hydrogen should be there. That's the blue. That's the hydrogen that should be blue. Now, why did the boron and the hydrogen add 100% cis?
There's no triangular intermediate.
No. You're correct. But what is there?
Square.
There's a square transition state. Well, a square transition state is going to be really difficult to stretch the square so that one group is above the double bond and the other group is below the double bond. Squares don't work that way. Neither do pentagons. Just for future reference. So you're correct. There's no triangular intermediate, but now what there is a square transition state where basically we got a double bond. We have to plot both things on one side or the other, but we can't mix and match because it's not a two-step mechanism. It's just one. So we've got to add both things to the same side. And when we do that, we add the H and the Br, or H and the boron to the same side. and then the peroxide just replaces the boron with an OH. So that's why it's 100% cis. Okay? So what's the last question I got to answer? Why is it? Why is it what? I got the stereoselectivity taken care of, right? I've got that explained, at least to myself. Now what do I need to explain? Thank you, the regioselectivity. Well, what regioselectivity is this? This could be regioselective, but what does it go by? Markovnikov or anti-Markovnikov? Anti. So now I got to explain that, right? Okay, so it turns out that this is totally based on sterics. The boron is going to be a fairly large group, even though it's BH2. You go, that's not that big. Well, I'm kind of cutting some details out of the mechanism here, which I still will. But just accept for the sake of argument that boron's a big group. So if I'm adding the boron, which one am I going to add to? I'm going to add to the one that says in pink, least sterically hindered alkyl borane. So if I add to the primary carbon, then I end up with something that's less sterically hindered than adding to the secondary carbon. So this mechanism turns out to be based on sterics. It's 100% cis, but it's also anti-Markovnikov because in the end, that boron is replaced with, this boron is replaced with an OH, and so the H ended up adding to the carbon with the least amount of hydrogens, and the OH added to the one with both, or with the most, which is anti-Markovnikov. Okay. And if you want to see that, there's a pseudo picture of what it looked like, although, like I said, I'm kind of leaving out some critical parts of the mechanism. So there's the end. 3 ways to add H and OH to a double bond. Right. So we'll talk about epoxides when we get back.